you're having trig problems, I feel bad for you, son. I got 9 problems, but trig ain't one.
But actually, 2.6 is 3 problems. 3 problems.
I don't like to think of there as being problems, only opportunities.
Well then, let's take this time to figure out 2.6 multi-triangle opportunities.
Okay.
So, whenever we get one of these opportunity-solving moments, there's a couple of things that we might need to do. We should note the information that we have, because we will always be provided with some information. Next, we're going to find out what information we need and that's missing. Then we're going to try to find a way to determine that missing information, and then determine what information we could find using that. So, some information in these multi-triangle opportunities might not necessarily give us an immediate pathway to the final answer, right? So, what we can do is looking in these opportunities is seeing what common sides these triangles might have, or common angles that these triangles might have, because that might lead us to better solve the problem. Okay? So we're going to better solve the opportunity. I'll slip with a tongue there. Whew. So we're going to take a look at this one here. So we're trying to solve for theta, okay? And we're trying to solve it for the nearest tenth of a degree. Now, a couple of things that I know that we've learned is that I can use my trig ratios for right angle triangles, my SOHCAHTOA, if you say. But when I notice my SOHCAHTOA, I need to have 2 side lengths if I'm trying to solve for my angle there, right? And in this case, I have 1 side length, but I don't have either of the others. So in order to solve for angle theta, we're going to need one of those other sides. Well, and we could try and solve for the hypotenuse, but there's really no other information we could use to solve for that hypotenuse. There's not, something else that's here that we can use. There's not anything at all, actually. But if we're looking at this side length here, what's nice is there's another triangle attached to it. Right? We have this triangle over yonder. Now, if we're looking at this triangle here, it looks like we have quite a bit of information. We have this 30-degree angle. We have the hypotenuse of this triangle. And we can solve for this side length. That's not a bad idea. And then once we have this side length, it could help us find our original, our goal, and that's to solve for theta. Okay, so that's going to be our game plan here. So let's take a peek. I'm going to label this side length with some variable of my choosing. I'm going to choose x, just so that we have, some sort of reference point to name that guy. Right? We could call this side length x, and it'll be x in both this triangle as well as this larger triangle, because they are same.
And it's very important that we actually put that x there, because if x just suddenly starts appearing in our work and we haven't defined it somewhere, that's actually a communication error. So the fact that x has been placed there means that it has been established.
Good point. Alright, so we're going to start by solving for x using the information in this triangle here. And in this triangle here, we have our given angle of 30 degrees. In relation to that 30 degrees, 12 would be considered our hypotenuse, and x would be considered our opposite. Because we have our opposite and our hypotenuse, we're going to be using our SO of our SOHCAHTOA. And so we're going to use sine of 30 degrees is going to be my opposite, which is x, over my hypotenuse, which is 12. Now to get x alone, I'm multiplying both sides by 12, so I end up with x is equal to 12 sine of 30 degrees. And when I beep boop bop that onto my calculator, I get x is equal to 6 exactly. But this is not my final answer. That's just the first step in solving my opportunity. The next thing I need to do is take a look at, what color am I going to use? This one. That x value to help me solve for the angle theta in this triangle here. Okay. as I do that, I notice that my theta here is my angle. In relation to theta, 17 is my adjacent. And in relation to my theta over here, x is still considered my opposite. Keep in mind that when I'm dealing with two triangles, sometimes both of these sides will both be considered the opposite. But sometimes in relation to where they're positioned in the triangle and the angle you're trying to solve for, they might be different. They might be an opposite and a hypotenuse. They might be opposite and adjacent. So it's always important to kind of label it in respect to the specific triangle you're talking about. Okay? So a little bit of a tip there. Now I'm going to go ahead and solve for that theta. And I have my opposite and my adjacent, so I'm going to use the TOA of my SOHCAHTOA. So I have tan of theta is equal to my opposite, which is that value of 6, because we just solved for 6 for x, over my adjacent, which is 17. Now, there we go. To get my theta alone, I'm going to inverse tan both sides. So I'm going to get theta is equal to the inverse tan of 6 over 17. And keep in mind that those brackets around 6 over 17 are crucial. And when I beep, boop, bop this into my calculator and I'm rounding to the nearest tenth, I'm getting 19.4 degrees. And there we have it.
And next up, we have an opportunity to put these kind of things into context. So in this case, we've got a tower. We've got some descriptions about some guy wires that are holding this tower up. And we're going to have to find some information about that. But given this contextual opportunity, it might be good to draw ourselves a diagram. So my tower exists. Whee! What an excellent tower. And it's got some guy wires that connect it into the... Nobody's turf is that color. Into the ground. We've got one that's 24 meters long. It makes an angle of 45 degrees with the ground. Okay, I can draw that. No sweat. Looks like that. It's 24 meters. It makes an angle of 45 degrees with the ground. Super. And one that is 20 meters long. Oh, here's a big question. Is that going to be more like over here? Or is it going to be going that way? That's something that should be worth considering. See if you can figure it out. Pause if you have to. I'm continuing now. I'm thinking to myself, if I put it this way, if it's on the other side of that anchor point, that has to be a longer wire. There's no way I can be further away and be using a shorter wire. So if this other wire is 20 meters long, it must be a bit more inside. So there's my 20 meter wire. And we need to find how far apart these wires are anchored in the ground. So we've got anchor 1, anchor 2, and that's the distance we're trying to find. If you think you know how to solve this, go ahead. I dare you.
Ooh.
In fact, I double dare you. Maybe even triple dare. Maybe that's as high as I'll go. So we need to figure out some stuff here. I'm thinking that this triangle right here is not a right triangle. And since it's not a right triangle, I can't just say, oh, well, I've got this angle and this side length, and I'll solve for this other side length. No. That only works for right triangles. I do have a couple of right triangles, of course. Boop, boop. There's my right angle. So I've got this triangle here, and I've got this triangle here. The stuff that's common with that and our target, D, would be these sides here. So if I can find this little length of X from there to there, and I can find this whole length, let's call that Y, then the difference between those would be D. Super duper. Maybe I'll just get right on finding that. I'll start with finding y. So in finding y, I'm using that triangle there, and in I go. So for y, I can say that that's the adjacent angle to this 45 degrees. And with this 24 being a hypotenuse, I'll be using cosine. So the cosine of 45 degrees is y over 24. Y is equal to 24 cos 45 degrees. And according to some quick mental maths, that's about 16.971 meters. I know we only need to go to the nearest tenth in the end result, but to make sure I'm actually accurate to the nearest tenth, I'm going a couple extra here. That's that business. Complete. All right, now we find x. And we'll use this 20-meter hypotenuse, and then we'll use, oh my gosh, we have nothing else. We have no angle here, no angle here. We don't have this side length. Rip. All's not lost. We can find this common side length between the two triangles. We just have to give that a label of some sort. I'll call it h. H for the height of the tower, if you will. Finding h. There's a couple ways to play this. First of all, you could say that the sine of 45 degrees is its opposite side, which is h, over the hypotenuse, which is 24, and solve for h that way. But it's worth noting that if this is 45 degrees, so is this, and that's an isosceles triangle, which means that this whole side and this whole side actually have to be the same. So interestingly enough, when you find h, you will still get the same value as y. It's 16.971 meters. Shaboom. Well, time to find x. And for x, I don't have any angles in that triangle, but I do have two sides. So they're all linked with our good friend Pythagoras. And I can say that x squared is 20 squared minus our value of h squared. Plugging those things in, I get x squared to be like 111.9851559. That's having plugged in 20 squared minus this number squared into my calculator. And you should have buttons on your calculator allow you to use your most recent answer. So you can say like 20 squared minus ands squared. It might be attached to your equals button or something, but just figure out where that is so you can do this more easily. Any poops. X must be then a little bit more than 10. Calculator wise, we're looking at 10.583 meters. This has been a doozy so far. We're not even done. All we have to do though is find d, and we said that d is the difference between y and x. Here we go. Oh, I need a new color altogether. So finding d is y minus x, which in this case is about 16.971 minus 10.583, giving us a value rounded to the nearest tenth, still that, of 6.4. Now this is a contextual opportunity, so we should present our results in context. Oh, sorry, we have all our magic colors on the side. But I wanted this again. So, we'll have to state where the y's are anchored. Anchored about 6.4 meters apart. That was a doozy, but this one is G-O-N-E done.
Okay, for this question that Mr. Athide just finished, it is a lot of work. Yes, we totally understand that. But if you were able to draw the opportunity out in diagram form, kind of go through the steps and say, what do I need? What do I need? What do I need? You will always be given enough information, and the problem is always solvable. It just sometimes takes more mental, just mental power than you might be willing to give at that individual point in time. So just power through it. Try your best. Don't give up. You got this.
There's always information you can find with those triangles. Just go through it, figure out which information you can find, and which of that information will actually help you on your quest.
Okay, so taking a look at opportunity C, the last opportunity of this section. From the top of the Rockefeller Center in New York, one can see the Empire State Building. All right, so Rockefeller Center. Okay, an Empire State Building. I think it looks something along the lines of this. I don't know.
Oh, yeah.
It has kind of like a...
It's got like a pointy tip. Yeah, it's got its party hat.
Something like that. And I do that a little bit too tall, so we're going to shrink this baby down. I said we are going to shrink this baby down. And we're going to move this one so they're ish level. And, of course, New York being a concrete jungle, there's no grass. It's just a big slab of cement connecting the two of them. And here you are on the top of the Rockefeller Center. Boop, 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 boop. And you're not naked because that's public indecency. Yay!
But dang, you're tall.
You're huge. But you have cool blue hair. All right. So from the top of that, you can see the Empire State Building. The bottom of the Empire State Building can be seen by looking at an angle of depression of 10.76 degrees. Okay. Well, remember, angle of depression goes from your horizon, which is a horizontal line from your eyeballs, and down to your line of sight. Whoa, I definitely thought that was going to turn out straight.
I thought so too.
Come on, bro, what you doing? Actually, that's not bad. I'll keep it. And that angle of depression occurs between the two of them, so that 10.76 degrees happens here. It does not happen here. All right, poofed. And then we can see the top of the Empire State Building by looking at an angle of elevation of 7.21 degrees. So now from my eyeballs to the top, here we go. That angle of elevation is 7.21 degrees. Now, the height of the Rockefeller Center, that whole thing there. Oh, not the Rockefeller Center, is this one. Is 266 meters. All right. Determine the height of the Empire State Building to the nearest whole meter. So we want to figure out this. To the nearest whole meter. Now, we can see that we have two different triangles, right? We have this one here, which is a right angle triangle formed with my angle of elevation there. And we have this triangle here that I formed with my angle of depression. I want to figure out this whole height. Well, what you might notice is, because I have two triangles, I can find this piece of the height, which is x, and I can find this piece of the height, which is y, and add them together to get my height of the Empire State Building. So we could say h is x plus y. Now, in the question, we were given that the Rockefeller Center is 266, and that's going to be the same as my x value. Nice. Okay. So I actually already know what that x value is. Whoa, what is it? 266? What the heck? Nice. So instead of having x there, I can put 266 plus y. All right. So now we journey to find y. And to find y here, I'm going to be looking at the information in this triangle. But that triangle so far doesn't have enough information there. Right? I only have an angle. I don't have another side length that I could use. So, pretty sad, but not too sad, because I noticed that in this triangle here, maybe I could find this common side length, this one over here, because I have enough information on my bottom triangle, and to find that common side length will help me with my top triangle. Okay? So I'm going to label that, and I'm going to label that common side length D, because it's the distance between the two buildings. Right? You don't have to call it D for that distance. However, sometimes giving it a variable name that relates to what's actually happening contextually could help you better understand the opportunity at hand. Okay, so let's go ahead and solve for D. All right. Well, I can actually solve for D, just so if you ever look back, you know what we're doing here. Okay, so in this D solving process, we're looking at this purple triangle at the bottom. We have a 90-degree angle there. Life is good. In relation to my angle, I have my opposite side length, and I'm looking for my adjacent. So I'm going to be using the tan ratio. So I have tan of my angle, which is 10.76 degrees, is my opposite, 266, over my adjacent, which is x. Now I can't solve for x when it's in the denominator, so I'm going to multiply both sides by x to bring it to the top. And now to isolate for x, I'm going to divide both sides by tan of 10.76 degrees. So I will get x is equal to 266 divided by tan of 10.76 degrees. Now when I beep boop bop that into my calculator, I am going to get 1,399.729 meters. Ooh, baby. So now I have my value for D. And by using that value for D, I could actually now solve for y. Solve for y. Now in solving for y, I'm going to use this angle here. In relation to this angle, my y is going to be my opposite, and my D is going to be my adjacent. So again, I'm going to be using my tan ratio. So I have tan of my angle, which is 7.21 degrees, is equal to my opposite, which is my y, over my adjacent, which is that 1399.729. Now to get y alone, I'm going to multiply both sides by my denominator, so I'm going to get y is equal to 1,399.729 tan of 7.21 degrees. And when I plug that into my calculator, I end up with 177.075 meters. Just as one thing to notice, or actually two things to notice. So the first one being I've kept a couple extra decimal places here because we want to figure out our height. Does it say? To the nearest whole meter. There we go. So we're always going to keep a few extra decimal places just so that we don't goof that accuracy portion. Another thing to keep in mind as we're doing this, make sure that you have your degree signs all the way through, because it is very, very crucial for your work to help distinguish a side length from an angle, and we do that by using a degree.
So noting there, we're not just putting degree signs on everything that exists, only on the angles.
Yeah, it wouldn't make sense to put degrees on the 266 because the 266 represents a side length, and side lengths aren't given to us in degrees.
No.
All right, but we're not quite done the problem. We have to figure out our height. And our height was in pink. Our height we determined would be our 266 plus y. So 266 plus 177.075 is 443.075. Because this is a contextual opportunity, we have to respond in a contextual-like manner. So, we will say that the height of the Empire State Building, my writing's getting a little bit gross, is about 443 meters tall. And remember that is to the nearest whole meter.
That's pretty tall.
Yeah.
That's taller than me.
Just a little bit. So there are some practice textbook opportunities for you to take a look at. Because contextual opportunities can sometimes be a doozy, it is worthwhile to take a practice or take a peek at those. You will get some additional work in class, but if you're ever struggling, practice makes perfect.
There's also a quiz coming up, as you can see by the fact there's a quiz point there. You'll want to be certainly ready for that. That covers everything from 2.4 to 2.6.
And we'll be talking about when you could expect that in our next class.
That's about it. Adios, muchachos.
Hey, that's my line.